In the last video, we said that we can visualize the variation in our temperature by looking at the spread, so how much the data spreads. And for Provo, we said that the distribution for daily maximum temperatures is approximately normal, so it follows that bell-shaped curve. And whenever we have data that is approximately normal or bell-shaped, we typically find the mean value to be in the center of the distribution. So recall that the mean temperature for Provo was 67 degrees. So 67 degrees is in the center. But we also saw that the daily high temperatures for Provos varied quite a lot from the mean temperature. And so we can see here that the range is relatively large, especially if we compare it to San Francisco. And specifically, we can calculate that variation by calculating the standard deviation for the sample. So when we look at all the daily maximum temperatures for Provo over a year, so data was collected for 365 days, we saw that on any typical day, the temperature varied from the mean temperature by about 21 degrees Fahrenheit. So when we have a distribution like this, we can calculate probabilities, and probabilities help us answer questions like what I have posed here. Is it unusual for the temperature to be above 85 degrees Fahrenheit for each city? So let's first look at Provo here. If we mark where 85 degrees is, that's approximately here, so I'll mark it in blue, 85 degrees, and take a look at how many days out of 365 days the temperatures were above 85 degrees, we can see that that data was collected and reflected in these frequency bars that I'm highlighting in blue here. So I can answer this question by calculating a probability. So I want to know, what is the probability that if I pick a random day out of the year, what is the probability that the temperature of that day, so I'll call that X, the temperature of that day is greater than 85 degrees Fahrenheit? And to calculate that probability, we can calculate a ratio, because that's what a probability is. And so that ratio is the number of days where the temperature is above 85 degrees out of the 365 days, which is the sample size. So here, I'm going to just do a rough calculation here by eyeballing the frequency distribution below. So this first bar here looks like maybe around 18 days, the temperature was between 85 degrees, and that looks like maybe 88 degrees. And then the next frequency bar, that's approximately 45 days. And then this looks like it's approximately 35 days, 10 days, and 5 days. So if I add 18 plus 45 plus 35 plus 10 plus 5, that gives me 113 days. So if I take 113 days and divide it by 365, that's approximately 0.31 or 31%. So we can see that there is a probability of about 31%. So there's a 31% chance that if I pick any typical day in Provo, Utah, the temperature is going to be greater than 85 degrees. So is it unusual for the temperature to be above 85 degrees? Well, the answer to that question is can be more objective if we look at the probability. So here, if I'm being subjective, I would say that it's probably not unusual, because 31% seems like a pretty high percentage, okay? But again, we have to be a little bit more subjective about this. So there is a rule, and we talked about this in chapter 1, that determines whether or not the results of a study are statistically significant or not. And that rule applies here as well. So if you guys recall, we said that the results of a study are statistically significant if it has a low probability of occurring. And we said we define low by using the criterion that the probability of it occurring is 5% or less. Okay, so here, because 31% is higher than 5%, we can see that the probability that the temperature is going to be above 85 degrees is not unusual, okay? It's not significantly high or low, because it is more than 5%. So another way for us to calculate probabilities when we have data that's normally distributed, so again, make a note to yourself that this only applies to data that has a normal distribution. So for normal distributions, we can estimate probabilities by using a rule called the empirical rule. And the empirical rule is just a rough guideline. So it's a rule of thumb that helps us um, understand how the standard deviation measures variability, and then also gives us a tool to make rough estimations, okay? And what I mean by that is this. So we can still answer this question, right? Is it unusual for the temperature to be above 85 degrees by looking at how much the data varies from the mean? So here, what I have on the right is I have a normal distribution, a bell-shaped curve. And in the center of the distribution, I'm going to mark the mean for Provo, okay? So the mean temperature is 67 degrees. Now, on a normal distribution, we can calculate temperatures that are 1, 2, and 3 standard deviations above the mean, and then 1, 2, and 3 standard deviations below the mean. So temperatures that are below the mean, we identify them with a negative number, okay? And when we talk about the standard deviation. And so if we're at the mean, then we are 0 standard deviations from the mean because we are at the mean. So using a standard deviation of 21 degrees, I can calculate the temperatures, again, that are within 1, 2, and 3 standard deviations from that mean. So to calculate the temperature that is 1 standard deviation above the mean, that's just 67 degrees plus 21 degrees. And so that gives us 88 degrees Fahrenheit. So this marking here is going to be 88 degrees Fahrenheit. And then to calculate 2 standard deviations above the mean, that is going to be 67 degrees, right, times, so that would be 67 degrees, right, plus 2 times the standard deviation, right? So the standard deviation is 21 degrees Fahrenheit. So if I'm 2 standard deviations above the mean, that's 21 degrees times 2 plus 67, which gives me 109 degrees Fahrenheit. And then to calculate 3 standard deviations above the mean, that would be 67 degrees plus 3 times 21 degrees, which gives us 130 degrees Fahrenheit. So I'm going to do the same thing to the left here, but instead of adding, I'm going to subtract. So temperatures that are 1 standard deviation below the mean, that's going to be 67 degrees minus 21 degrees. So that gives me 46 degrees Fahrenheit. And then temperatures that are 2 degrees below the mean, that's going to be 67 degrees minus 2 times 21. So that gives me 25 degrees Fahrenheit. And then 3 standard deviations below the mean, that would be 67 minus 3 times 21 degrees. That gives me 4 degrees Fahrenheit. So here we can kind of mark temperatures that are 1, 2, and 3 standard deviations away from the mean. And if we take a look at this, the empirical rule tells us this. The empirical rule says if you take your data that's normally distributed and you look at temperatures that are 1, 2, and 3 standard deviations from the mean, you'll see that temperatures that are within 1 standard deviation, you're going to capture about 68% of your data values. Okay, so in this example, that means that out of 365 days, we can expect that 68% of those days, the temperature is going to be within 1 standard deviation of the mean temperature. When we move out 2 standard deviations, we're going to capture approximately 95% of our data value. So approximately 95% of the daily temperatures in Provo are going to be within 2 standard deviations of the mean. And if we go out 3 standard deviations, then we will capture almost all of the data value, so 99.7%, okay? And so again, roughly, I'll mark it out, okay? So 1 standard deviation from the mean. So that means that temperatures that are between 46 degrees Fahrenheit and 88 degrees Fahrenheit, that's going to be approximately 68% of my data values are going to fall in this area under the bell-shaped curve. Okay, and you can roughly estimate that. So here, if I mark 46 degrees, that's there, 46 degrees, and 88 degrees is about here. So if I go from here to here, okay, and add up all these frequency bars represent the number of days where the temperatures were between 46 degrees and 88 degrees. You'll see that the frequency bars here, when I add them up, they're it's going to equal approximately 68% of the 365 days, okay? And then I'll use green here. If I go out 2 standard deviations, so 2 standard deviations, we're looking at temperatures that are between 25 degrees Fahrenheit and 109 degrees Fahrenheit. Then you'll see that that includes the 68%, and then we go out a little bit further, and then this part of what I'm shading under the curve represents 95% of the daily temperatures. Okay, so 95% of the daily temperatures in Provo are going to be between 25 degrees, so 25 degrees here, and 109 degrees, which is somewhere out here. Okay, and again, this is a rough estimation. Okay, and then we can see that if we go past, so this is the important part here. If we go past 2 standard deviations, okay, so if we go past 2 standard deviations, then you'll see, I'm going to shade in red here. You'll see here, this is the remaining, if we take a look at the remaining percentage, that would be the remaining 5%. So because a normal distribution is symmetrical about the center, this area here, if I take 5% and split it equally in half, that's approximately 2.5%, and this is approximately 2.5%. So what this tells us is it tells us that anytime you have values that are 2 or more standard deviations above the mean, right, those values are going to be considered unusual, okay, or statistically significant. Okay, we can also say that those values are significantly high or significantly low. So in this example here, if we look at temperatures that are 2 degrees above and below the mean, that means that temperatures that are above 109 degrees Fahrenheit are going to be unusually high or significantly high. And temperatures that are below 25 degrees Fahrenheit, those temperatures are also considered unusual and significantly low because there is a 5% or less chance. Okay, so here we can see that's only 2.5% and 2.5%. So it's less than 5% chance that a temperature in Provo is going to be more than 195 degrees or less than 25 degrees Fahrenheit. So that is the more subjective way for us to define values that are considered unusual or statistically significant or significantly high or significantly low. Is that criterion that the likelihood of getting those values is 5% or less. So if we go back and try to answer this question again, but this time using the empirical rule, you'll see that we'll get something close to 31%, but it's going to be off a little bit just because if we take a look at the actual data values, you can see there that we've got these 2 tall frequency bars that clearly do not fit under the curve. So let's just do a rough estimation using the empirical rule to see what probability we would get for temperatures above 85 degrees. So I'm going to mark in purple here on the normal distribution on the right. 85 degrees is approximately there. So if I want to figure out what is the probability that the temperature is going to be above 85 degrees, I'm looking for the area that is shaded in purple here. So we can see that I've got in red here 2.5%, and then I'm going to add that to, so this portion here that I'm shading here, that's approximately 13.5%. And how I got that is just, I know that values that are 2 standard deviations from the mean, so between 109 and 25 degrees Fahrenheit, that's 95% of the data values, but temperatures between 46 degrees and 88 degrees, that's 68% of the data values. So if I subtract 68 from 95, that gives me the purple region that I just shaded in the right here, and then also I'll just shade real quickly on the left here. This other purple region on the left, which is 27%, and then I divide that equally, so each purple shaded region on the left and then right is approximately 13.5%. And then I've got this little portion right here. So that is approximately 10%. Okay, so if I add another 10% here, this gives me roughly 26%. So I know that 26% is not very close to 31%. And the reason why it's off a little bit is because the actual data value here, we see that the distribution for temperatures in Provo doesn't really fit that normal shape that well. So you'll see that these two estimations here are going to get closer and closer together when our distribution looks more approximately normal. And so in the next example, when we look at the temperatures for San Francisco, you'll see that those estimations get closer to each other because San Francisco's data is definitely more bell-shaped than Provo's temperature. And that's also because the standard deviation is smaller. So let's take a look at the distribution for maximum temperatures for San Francisco and try to answer the same question. Is it unusual for the temperatures to be above 85 degrees? So again, we want to make a note to ourselves that the distribution is approximately normal. And again, we said that for Provo, the data does appear to be more normally distributed. So we've got a normal distribution here. And the variation in the data, so the variation in the temperature is smaller, and we can also see that by looking at the standard deviation, 8 degrees Fahrenheit compared to Provo's 21 degrees Fahrenheit. 8 degrees is definitely smaller. So we can see here that the mean is in the center, so X bar of 65 degrees is in the center, and the standard deviation of 8 degrees tells us that on any typical day, the temperature varies from that mean temperature by only about 8 degrees Fahrenheit, and so that's why the spread is much smaller. So I want us to, again, roughly estimate what's the probability that the temperature is above 85 degrees. So if I mark 85 in black here, 85 degrees is about there. So if I want to do a rough estimation, I can count these frequency bars. So this looks like that's about 10 days and that's about 5 days. So out of 365 days, 15 of those days we have temperatures that are above 85 degrees. And that gives us a probability of approximately 0.04. So that's about 4%. And 4% is definitely less than 5%. So if we use that criterion that says that if the probability of getting a certain data value is 5% or less, then we say that it is unusual or statistically significant. So here for San Francisco, I would say that it is unusual for temperatures to be above 85 degrees Fahrenheit because the likelihood of temperatures being above 85% is only about 4%, which is less than 5%. And so again, let's use the empirical rule. The empirical rule, which tells us that if temperatures are 1 standard deviation from the mean, that will capture about 65% of our data. About 95% of our data is going to be within 2 standard deviations from the mean. And if we go out 3 standard deviations from our mean, we will capture almost all of our data values. So real quickly here, I'm going to translate this normal distribution to this bell-shaped curve where I'm going to mark my mean value. So your mean value is always in the center of your distribution, 65 degrees. And if you're in the center, you're the mean, you're 0 standard deviations from the mean. And then we want to see what temperatures are 1 standard deviations from the mean, 2 standard deviations from the mean, and then 3 standard deviations from the mean. Okay, and again, we have to use our standard deviation of 8 degrees. So to calculate 1 standard deviation, that's 65 plus 8 degrees, which is 73 degrees, right? And then 65 minus 8 gives us 57 degrees on the left. And then if I go 2 standard deviations, all right, you can actually just start with, okay, well then that's 73 degrees plus another 8 degrees, which gives us 81 degrees. And then 57 degrees minus 8 degrees gives us 49 degrees on the left. And then 81 degrees plus 8 degrees gives us 89 degrees on the right. And then 49 minus 8 gives us 41 degrees on the left. And so here, if we use the rule that values that are 2 or more standard deviations above the mean or 2 or more standard deviations below the mean represent values that are significantly, so these values are significantly high, and then these values down here, right, that are less than 49 degrees, we would say are significantly low. Okay, all right, so Values that are significantly high or significantly low, meaning they are two or more standard deviations from the mean, right, have a probability of about 2.5% chance. So 2.5 on that side and 2.5 on this side, which makes up 5%. So the probability that temperatures are going to be above 81% is approximately 2.5%. So if I mark 85% on here, 85% is somewhere here. And so hopefully you can see that according to the empirical rule, the probability of temperatures being above 85 degrees Fahrenheit for San Francisco is extremely low. So the empirical rule would imply that this probability is actually going to be less than 2.5%. So definitely that would be less than 5%. So we would say that getting temperatures above 85 degrees Fahrenheit for San Francisco is unusual.